The year is 1964. The Cold War is not just a battle of ideologies. It is a battle for the stratosphere. The Soviet Union is advancing its surface-to-air missile technology, threatening the efficacy of the massive American B-52 fleet. In response, the United States Air Force initiated a project that would become the ultimate expression of 1960s aerospace technology, a strategic bomber that redefined speed, altitude, and cost. This was the North American Aviation XB-70 Valkyrie. The concept was simple in its ambition and terrifying in its complexity. Build an aircraft capable of flying at Mach 3, 3 times the speed of sound, at an altitude of 70,000 feet. At that height and speed, no contemporary Soviet interceptor could reach it, and no missile could track it. The Valkyrie was designed not to sneak past defenses, but to outrun the future. It was intended to be the successor to the B-52, a fleet of 50 bombers that would dominate the global stage for the rest of the 20th century. The initial cost projections were astronomical. By the time the first prototype was completed, the development cost had soared to the equivalent of over $750 million per aircraft, a sum so immense it became a political target before the Valkyrie ever reached its intended operational altitude. This project was a collision point between engineering genius and economic reality. The Valkyrie was born of the certainty that speed and altitude offered invulnerability. Yet, even as the first prototypes were taking shape in the massive hangars, a fundamental shift in Soviet defense technology, a shift from high-altitude interception to low-altitude missile defense, was already rendering the XB-70's core strategic premise obsolete. The story of the Valkyrie is the story of a technological masterpiece canceled, not by failure, but by a geopolitical pivot that happened too quickly for the billion-dollar prototype to catch up. The engineering problems were solved, but the strategic problem became unsolvable, leaving the world with the fastest bomber that was ultimately too slow to adapt, to achieve, and sustain Mach 3 speed. The XB-70 Valkyrie could not rely on traditional aerodynamics. The design required a revolutionary solution to minimize drag and maximize lift in the thin, high-altitude atmosphere. This solution was the application of compression lift. This was the true engineering genius of the Valkyrie. At supersonic speeds, the shock waves generated by the front of the aircraft are not merely resistance. They are a controllable force. The XB-70's massive delta wing design and its massive squared-off air intake ramps were meticulously engineered to channel the high-pressure shock wave beneath the wings. Think of it. The aircraft was designed to ride its own shock wave. The energy that normally causes drag was intentionally trapped, creating a high-pressure cushion that provided up to 30% of the aircraft's lift at Mach 3. This revolutionary concept allowed the Valkyrie to be more efficient and carry a heavier load at extreme speeds than any previous design. Furthermore, the Valkyrie featured massive, hinged wingtips that could be hydraulically lowered up to 65 degrees. When flying at Mach 3, these drooped wingtips performed two critical functions. They reduced drag and helped maintain directional stability, acting like massive vertical fins. They also helped contain the compression lift cushion beneath the main wing. However, these complex, moving surfaces were under immense thermal and mechanical stress, requiring exotic materials and constant, painstaking maintenance. The engineering was magnificent, but the very complexity required to defeat friction created a maintenance nightmare that foreshadowed the project's economic demise. Sustaining Mach 3 is not just a problem of thrust. It is primarily a problem of heat. Flying at triple sonic speed at 70,000 feet subjects the aircraft's outer skin to intense kinetic heating. The surface temperatures of the Valkyrie's leading edges could soar above 330 degrees Celsius, 626 degrees Fahrenheit, hot enough to melt conventional aluminum alloys. The XB-70 required a radical shift in construction materials. The Valkyrie could not be built primarily from aluminum like its B-52 predecessors. Over 90% of the airframe, particularly the wings and nose, was constructed from brazed stainless steel honeycomb paneling and titanium alloys. Brazing, a high-temperature joining process, was essential to fuse the steel panels into a strong, heat-resistant, lightweight structure. This choice of material was the largest contributor to the project's staggering unit cost and its prolonged development timeline. Working with titanium and stainless steel honeycombs was immensely difficult, requiring specialized tooling, pristine cleanroom conditions, and entirely new fabrication processes. The engineers were essentially pioneering the field of high-Mach metallurgy as they built the plane. The Valkyrie was a technological bridge between the early jet age and the future of hypersonic flight. Its design informed later, more successful Mach 3 programs like the state Route 71 Blackbird. But the constant battle against heat expansion and contraction demanded unprecedented manufacturing precision. The slightest imperfection in a weld or braze joint could lead to catastrophic structural failure at Mach 3. The engineers conquered the heat barrier, but in doing so, they created a financial barrier so high that the Air Force could afford prototypes, but never a full fleet. The ultimate strategic demise of the XB-70 Valkyrie was sealed, ironically, by the success of a defensive weapon, the Soviet S-75 missile system, NATO codename SA-2 guideline. When the Valkyrie program was conceived in the mid-1950s, the assumption was that altitude equaled safety. The XB-70's Mach 3 speed at 70,000 feet was designed to be untouchable. However, the 1960 shoot-down of France's Gary Powers U-2 spy plane over the Soviet Union by the S-75 missile shattered this premise. The U-2 was flying below the XB-70's planned operational altitude, yet the missile successfully proved that Soviet SAM technology could reach and destroy high-altitude targets. The strategic conclusion in the Pentagon was immediate and brutal. The age of high-altitude strategic bombing was over. The new paradigm shifted to low-level penetration. Military planners determined that bombers needed to fly extremely fast, but right on the deck, hugging the terrain at altitudes below 1,000 feet to evade radar detection. The XB-70, designed for the thin air of the stratosphere, was optimized for speed and lift at high altitude. It was structurally and aerodynamically unsuitable for sustained, high-speed, low-level flight. The Air Force realized that the multi-billion-dollar XB-70 fleet would be vulnerable to a low-level missile defense system as soon as it slowed down to refuel or was forced to descend. The massive cost of the Mach 3 technology could no longer be justified when the mission profile fundamentally changed. The XB-70 was a technological answer to a strategic question that the enemy had already changed, leaving the world with an incredibly fast bomber build for a war that was already obsolete. By 1961, the political axe had fallen. Secretary of Defense Robert McNamara, a ruthless proponent of cost-effectiveness, declared the Valkyrie redundant. He canceled the production contract, reducing the program from a planned fleet of 50 bombers to a mere 2 experimental prototypes, A/V-1 and A/V-2. The goal shifted from strategic deterrence to pure research and development, studying Mach 3 aerodynamics and propulsion. The 2 XB-70 prototypes were flown throughout the mid-1960s, providing invaluable data on supersonic flight, compression lift, and material science. The research was a success. However, the project was haunted by its own engineering complexity and cost, leading to an inevitable, fatal accident that on June 8, 1966, XB-70A/V2 was conducting a formation flight for a General Electric photo shoot, a routine PR mission involving 4 smaller chase planes. During the maneuver, one of the smaller chase aircraft, an F-104 starfighter flown by NASA pilot Joseph A. Walker, flew too close. The starfighter was caught in the powerful, massive wingtip vortex generated by the XB-70's enormous drooped wingtip. The F-104 was instantly flipped upside down, slammed into the XB-70's wing, and exploded. The massive Valkyrie, its wings severely damaged, continued flying momentarily before spiraling out of control and crashing, killing the co-pilot, Major Carl Cross, and the F-104 pilot. The loss of the second and final prototype was a devastating blow, not just in human lives, but to the research program. The accident was not a failure of the bomber's core design, but a tragic, violent reminder that even the most advanced, expensive prototype is vulnerable to the simple, unforgiving physics of close proximity, sealing the fate of the XB-70 forever in the archives of abandoned engineering. Achieving Mach 3 required an engine system of unprecedented power and endurance. The XB-70 Valkyrie was powered by 6 massive General Electric YJ-93 turbojet engines, each generating up to 30,000 pounds of thrust with afterburner engaged. This array of power was crucial for 2 reasons: reaching the operational altitude of 70,000 feet and overcoming the immense drag barrier to reach triple sonic speed. The engine nacelles were housed in a massive rectangular structure beneath the wings, integral to the aircraft's compression lift design. The engines utilized a highly complex variable geometry air intake system. At low speeds, the intakes were wide open. But as the Valkyrie accelerated past Mach 1, huge ramps and wedges inside the intake modulated the airflow, slowing it down to subsonic speeds before it reached the engine fans. This sophisticated engineering was necessary because the YJ-93 engines, like all turbojets, could not tolerate supersonic air directly entering the compressor stage. This system was an engineering triumph, but a logistical and maintenance nightmare. The precise choreography of the intake ramps was controlled by a complex set of hydraulics and computers, making the engine system one of the most failure-prone parts of the aircraft. A minor error in the ramp position at Mach 3 could instantly cause an engine unstart, a catastrophic shockwave that could stall the engine and potentially damage the entire engine base structure. Furthermore, the fuel consumption was staggering. To push 6 powerful turbojets to Mach 3 for sustained periods required massive amounts of high-performance jet fuel. The Valkyrie was designed to carry fuel tanks that consumed almost 80% of its internal volume. The concept of operating a fleet of 50 such aircraft, each requiring monumental logistical support and fuel, added another layer of prohibitive cost to the program, cementing the financial arguments against its full-scale production. The XB-70's advanced mission profile, flying at Mach 3 and 70,000 feet, often overshadows the massive engineering challenges faced during the simplest phases of flight, takeoff and landing. Because of its colossal size, nearly 190 feet long, and immense weight, over 500,000 pounds fully fueled, the Valkyrie required a massive, robust landing gear system. The gear itself was highly complex, featuring 18 wheels distributed across multiple main bogies. The complexity was driven by the need to absorb the enormous kinetic energy of landing a 250-ton aircraft, all while fitting neatly into the thin, heat-shielded wing structure. But the gear presented a serious dilemma regarding aerodynamics and heat protection. At Mach 3, every cubic inch of internal space was needed for fuel or engineering systems. Housing the massive gear required complex mechanical doors that had to seal perfectly to maintain the smooth aerodynamic profile. Any irregularity at supersonic speed would instantly compromise the airflow and the delicate compression lift system. Moreover, the gear itself was vulnerable to kinetic heating while retracted. Even though the gear was tucked inside the fuselage, the heat soaking into the titanium and steel structure was significant. Engineers had to develop specialized venting and cooling systems within the gear bays to prevent components from overheating and seizing. The landing gear, often an afterthought in aircraft design, became a multi-million-dollar engineering challenge in the XB-70. It was a constant reminder that no part of a Mach 3 aircraft could be considered simple, adding to the overall cost and complexity that doomed the fleet. The Valkyrie's fate was a perfect encapsulation of the brutal speed of the Cold War arms race. The XB-70 was conceived to counter the Soviet Union's early 1950s fighter interceptors. By the time the first prototype was rolled out in 1964, the Soviet Union had already moved 3 generations ahead in defensive capabilities. The Soviet answer to high-altitude bombers was the aforementioned S-75 SAM system, but also rapidly improving jet interceptors like the MiG-25 Foxbat. The MiG-25, developed in the mid-1960s, was itself capable of high-speed flight, Mach 2.8+. More importantly, the Soviet military realized that forcing an expensive Mach 3 bomber to constantly watch its flanks and monitor for missiles was the key to neutralizing its speed advantage. The shift to low-altitude strategy was solidified by the realization that missile technology was becoming exponentially cheaper and more reliable than building multi-billion-dollar strategic bombers. Why invest in 50 Valkyries when a nation could deploy hundreds of mobile, effective SAM batteries? The XB-70 became a victim of the missile gap argument, but in reverse. The Soviet missile advancements made the Valkyrie concept strategically obsolete before it was operational. The U.S. government could not justify building the bomber design for the war of yesterday, when the war of tomorrow required completely different capabilities. The Valkyrie was a magnificent technological relic of a bygone strategic era. The official cancellation of the XB-70 bomber fleet production in 1961 was a major blow to North American aviation and the U.S. Air Force Strategic Air Command, SAC. The decision, driven by McNamara's cost analysis and the strategic shift to low-level penetration, was framed as fiscally responsible, yet it sent a cultural shockwave through the aerospace industry. The Valkyrie represented the pinnacle of manned flight, the ultimate bomber. Its cancellation signaled the beginning of the end for the large, manned bomber as the primary weapon of nuclear deterrence. The future, the Pentagon declared, lay increasingly in intercontinental ballistic missiles, ICBMs, and smaller, faster, low-observable aircraft. The prototypes that remained became national symbols of ambition and technological achievement, attracting massive public and media attention. The sight of the huge, sleek, white delta-winged aircraft flying at triple-sonic speed was a powerful propaganda tool, even if the bomber mission was dead. This public fascination, however, masked the deep, internal division within the military about the program's worth. The tragedy of the 1966 accident, the violent mid-air destruction of a $750 million A/V-2 prototype, was devastating. The crash was visible for miles and resulted in the deaths of 2 highly experienced pilots. The human cost amplified the political vulnerability of the entire experimental program, leaving only the first prototype, A/V-1, to complete the remaining research flights. The loss was technically recoverable, but politically, it was the final, unanswerable reason to completely terminate all operational prospects for the true, enduring legacy of the XB-70 Valkyrie lies not in its brief flights, but in the technological data it generated, which was immediately transferred to one of the most successful and long-lived Mach 3 aircraft, the Lockheed State Route 71 Blackbird. The XB-70 program served as the massive, expensive testbed for the core engineering challenges of triple-sonic flight. Specifically, the Valkyrie pioneered 2 critical areas that the State Route 71 leveraged. 1. Titanium fabrication. The XB-70's experience in brazing and welding massive structures made of titanium alloys, a material notoriously difficult to work with, provided Lockheed engineers with a wealth of knowledge that was directly applied to the Blackbird's construction. Without the XB-70's metallurgical failures and successes, the SR-71's design would have been impossible. 2. Kinetic heating management. The Valkyrie established precise data on how heat expanded and contracted the airframe at Mach 3, proving that the aircraft could not be built traditionally. This informed the SR-71's radical design, which incorporated specific gaps in panels that only sealed perfectly once the aircraft reached high speed and temperature. The Valkyrie, though a failure as a bomber fleet, was a crucial stepping stone in the history of aerospace. It proved the concept of sustained Mach 3 flight, but its failures, primarily cost and complexity, taught the industry what not to do when designing the next generation of high-speed aircraft. The lessons learned were absorbed by the classified Blackbird program, ensuring that the XB-70's massive investment was quietly paid forward. The XB-70 was retired, but its technological ghost flew faster and longer than anyone could have predicted, Following the devastating loss of the XB-70A/V2 prototype in 1966, the entire strategic focus of the Valkyrie program shifted entirely to pure scientific research. With the bomber mission officially dead, the sole remaining prototype, I/1, was essentially turned over to NASA and the joint research efforts of the Air Force and the Federal Aviation Administration, FAA. The goal was no longer deterrence. It was knowledge acquisition. For the next few years, the XB-70A/V1 served as an irreplaceable, full-scale flying laboratory for Mach 3 aerodynamics, materials science, and atmospheric studies. This phase was crucial for proving the long-term feasibility of supersonic transport, specifically the commercial SST, supersonic transport, programs being considered at the time. The most valuable data harvested was related to the compression lift principle and the thermal effects of sustained high Mach cruise. NASA engineers meticulously instrumented the aircraft, gathering data on the stress, strain, and heat absorption across the titanium and steel honeycomb panels. This research was foundational, proving that a supersonic commercial airliner, despite the astronomical cost, was indeed physically possible. However, the research phase was extremely short-lived. The single remaining prototype was immensely valuable, yet immensely fragile. Each Mach 3 flight put phenomenal stress on the aging airframe and its complex engines. The cost of maintaining this sole prototype, with its unique fabrication methods and 6 thirsty turbojets, was financially unsustainable for a pure research role. The era of multi-billion-dollar research prototypes was drawing to a close, forcing a final, inevitable decision on the fate of the XB-70. The final chapter of the XB-70 Valkyrie is one of quiet, dignified retirement. Following the conclusion of its core research objectives, the Air Force, recognizing the immense historical and technological value of the single remaining prototype, moved to preserve it. On February 4th, 1969, the XB-70A/V1 took its final flight, a short hop from the Air Force Flight Test Center at Edwards Air Force Base to its final permanent home, the National Museum of the United States Air Force near Dayton, Ohio. The final landing marked the end of the world's most ambitious bomber program and the closing of a major chapter in the history of supersonic flight. The decision to preserve the aircraft was a deliberate acknowledgement of its status as a technological icon. The XB-70 was not merely a failed project. It was a time capsule of 1960s engineering philosophy, the belief that any problem could be solved through sheer scale, speed, and unlimited funding. It stands today as a massive monument to the strategic thinking that prioritized altitude and speed above all else. Its presence in the museum is a stark historical footnote. The world's fastest bomber, grounded by a missile that flew slower and higher than predicted, and a financial ledger that was impossible to balance. The cost of its development, over $1 billion for the 2 prototypes, was essentially the price paid for a massive, flying engineering textbook that ultimately served future, quieter programs like the State Route 71 Blackbird and the subsequent, unsuccessful American SST efforts. Had the XB-70 proceeded to full production, the operational reality of the fleet would have revealed catastrophic logistical and environmental flaws, reinforcing the wisdom of McNamara's cancellation. The Valkyrie was designed for its Mach 3 dash, but it was forced to spend most of its flight profile at subsonic speeds due to fuel consumption. Cruising at Mach 3 was a thirsty endeavor. For a global strategic mission, the bomber would have required multiple, complex mid-air refueling operations to reach its targets, significantly slowing the mission profile and placing immense strain on the supporting tanker fleet. Furthermore, the environmental impact of a fleet of 50 Mach 3 bombers was a growing, ignored concern. The sonic boom generated by the XB-70 at altitude was colossal, capable of damaging buildings and terrifying populations across the entire flight path. The noise footprint of the 6 YJ-93 engines, particularly during takeoff and sustained climb, would have made operating a large fleet from existing bases a continuous public relations and political nightmare. The most critical issue was the fragility of the full mission profile. A fleet of XB-70s would have been required to fly its subsonic legs into vulnerable airspace before accelerating. This vulnerability, coupled with the immense unit cost and the crippling logistical tail required for its exotic maintenance, meant the bomber was strategically unsustainable. It was a gold-plated solution to a bronze-plated problem. Beyond the strategic obsolescence, the XB-70 faced profound, inherent dangers rooted in the very advanced materials and aerodynamics that made it possible. One persistent engineering challenge was aeroelasticity, the interaction of aerodynamic forces and the aircraft's structural flexibility. The Valkyrie's massive, thin wings, built from brazed stainless steel, were designed to flex under extreme thermal and kinetic load. However, the engineers constantly battled the risk of flutter, a destructive, self-excited vibration of the wing at supersonic speeds that could rapidly lead to catastrophic structural failure. The tragic 1966 crash, while triggered by an external vortex, highlighted the inherent vulnerability of the aircraft's wing structure under asymmetrical stress. The wingtips, designed to fold down 65 degrees at Mach 3, were a critical example of this aeroelastic compromise. While they enabled compression lift and stability, the joint mechanism was constantly under immense pressure and thermal cycling. Any failure in the hydraulic system or structural fatigue in these complex, moving parts at triple sonic speed would have guaranteed the disintegration of the aircraft. The XB-70 was designed with an extraordinary low safety margin to achieve its performance goals. This trade-off between speed and structural forgiveness meant the aircraft was inherently unforgiving of minor errors or external forces. The project demonstrated that pushing the boundaries of Mach 3 flight required an unsustainable commitment to zero-defect manufacturing and perfect, continuous structural integrity across the entire airframe. The cost of this structural perfection for a fleet proved to be the final, unanswerable economic hurdle. The XB-70 Valkyrie remains one of the most powerful and visually stunning aircraft in history. It was a billion-dollar experiment that delivered exactly what it promised: sustained Mach 3 performance. Yet, it failed as a weapon system because the Cold War moved faster than even the fastest bomber could fly. The Valkyrie stands as a technological monument to a bygone era, proving that no amount of speed can compensate for strategic obsolescence or financial unsustainability. Its true success was providing the critical, hard-won data that made future, quieter programs like the State Route 71 and Concorde possible. It paved the way for supersonic travel, only to be retired before its time. The final question remains: was the XB-70 a necessary failure? Was the $1.5 billion spent on the prototypes worth the data that informed decades of aerospace design? The XB-70 Valkyrie was a magnificent six-engine prototype that was simply too fast for the military strategy and too expensive for the budget. The XB-70 was rendered obsolete by the cheap, effective SAM missile. Today, hypersonic missiles fly faster than Mach 5. Do you believe the future of strategic warfare will ever again see the development of a large, manned strategic bomber capable of surviving hypersonic speeds? Or has the missile definitively won the war against the bomber forever? Let us know your thoughts on the future of manned flight in the comments below.